All right, why are you studying mechanical engineering? Probably a lot of you, if you really reflected on it, would say, you know, I kind of got excited in this because of automobiles, cars, power, engines, rebuilding them, fixing them, playing with them. Other engines or other machines, maybe a motor of some sort. So we're finally going to touch on something. It's a review out of Thermo 1, at least the beginning of it, but we're going to focus on internal combustion engines for lecture 2. We're going to talk about the Otto cycle and the diesel cycle. You pop the hood, what do you see? Sometimes it's just a big black box. Some people that don't even know they need to check the oil. I encourage you to do a little bit more beyond what I'm going to cover and what's in the textbook. Go out to Wikipedia, take a look at their excellent web page, and go through it and just spend some time. But I encourage you to have a broader education and try to say, you know, fit this into the context of your world experiences and general knowledge about combustion engines and diesel engines. How many people have pushed one of these around in the yard? Sure. You ever wondered how it works? You know, you could take this class and then not even know how this thing works. It's a gasoline internal combustion engine. It's a lawnmower engine, true? And this illustration really shows what's the highlight right there, the crankshaft. Can you see the position of the crankshaft? What's connected at the bottom of the crankshaft? The blade that's twirling around, that you make sure you don't have any fingers or toes get anywhere around it when it's running. Because a lot of people have lost fingers or toes. They bend down and not think about it. And they put their hand in a place and it moves a little and away they go. So you got to be very careful because that twirling blade cuts the grass. But where's the piston? Where's the combustion? How many cylinders are in this? There's one cylinder, one piston, and it's actually going back and forth in this direction, right? Because it's connected to the connecting rod, and you can see the offset right here. You know what? People get rid of these as soon as they don't work. First of all, if somebody's giving one away because they couldn't start it in the spring, take it off their hands, drop the bowl on the carburetor, blow it out a little bit, put it back, and have a free lawnmower. True? So true. But the other thing is if they hit a stump, like this person right here just about hit a stump, the blade will look like something like this, and they throw it out for big item pickup. It's a perfect time to augment your university education with a little dumpster diving. Go out, grab the thing out of there, get some wrenches out of a garage, make sure you collect the oil or it's going to spill on the floor about a quart's worth. Take the thing apart and look at how it works. And don't worry about putting it back together. It was on the dumpster, it's going back out there. And the same people that were going to pick it up whole can now pick it up in pieces. And so there's a lot of people on the internet that have taken these apart and they just want to show you, hey, here it is. I've taken the bolts out of the head and here's the spark plug. Let's take a look at it, what it looks like on the inside. So if you don't want to get your hands dirty, which I encourage you to get your hands dirty, you can go ahead and, you know, take a look at the internet. Other things, a lot of friends, once they figure out you're mechanical or something, they'll one time somebody brought a brand new lawnmower. Maiden voyage through the yard, boom, hit a stump or something. They called me up. I said, you couldn't have bent the crank. I think I bent the crank. Go over there, sure enough, bent the crank. Trash, the whole thing. So brand new lawnmower, bent the crank. It's a perfect one to take apart. And a lot of fun taking those things apart. Do that. There's some animations. This one is a 4-stroke. There it's going. You've not seen a good animation on a 4-stroke cycle? I know there's 4 cylinders here, and they're in line. It's a little complicated to see. But the pistons are going up, down, up, down, up, down. Each time they go from the top to the bottom, that's a stroke. Then they go back up, that's another stroke. And to complete the cycle, if you just looked at this one, try to get the color changes. There's red, there's black, there's kind of bluish, there's red, there's black, bluish. But there's 4 colors they're showing. Well, they have the combustion, then expansion, that's power stroke. Then at the bottom, they're pushing out the exhaust, and then they're bringing in fresh air fuel charge. And then they compress that fresh air fuel charge, so there's really just 3 colors, right? because they bring it in and then compress it at the top, then they combust it. And you can see the little spark plug is a little pop right in here. And this animation's good. I encourage you to go look at other animations on the internet. So get out there, take something apart in the garage, as well as looking at animation on the internet. There's other animations. A lot of the animations are made by students or other people, and they're not perfect. If you look at some animations, this one's got a little issue with the rotation, the typical standard direction of rotation when you look at the front, looking at an engine down the axis. This one has a little issue with the valves, and this one also has a little issue with the counterweights. So be skeptical and question animations because they're just somebody put it together. But this is an excellent animation. What's the difference issue on the valves? Which valve is larger in the internal combustion engines? This is something that's not in the textbook. It's the intake valve. But you're going to see why, because when you crack open the exhaust, there's a high pressure and it goes pop. That's why we have mufflers. It can be very loud. Under a load, even without a load, it's not too bad, but I'm telling you, there's some people a mile away from my house in the middle of the night. They must not have mufflers. And they floor it, and I can hear them. Can you not hear them? You ever experienced that? And that's what the muffler's for. It's actually for that quick pop going across the exhaust valve. So the exhaust valve doesn't need to be that big to start getting a lot of stuff out. But the intake's the hard one for the engineer, to intake of fresh air-fuel charge. So the intake valves are large. This is a good view of a crankshaft. These are just beautiful, aren't they? Crankshafts. I mean, just gorgeous. I can stare at a crankshaft for hours. Oh, it's beautiful. And the machinists that work on them, rebuild them, turn them down. It's incredible, piece of art. Anyway, if you look at where the weight is, for, let's say, here, this is one right here. The weight's over here on that one. So it's kind of balanced. You want a balanced crankshaft. If you look at that animation carefully, it's kind of the weights are on the other side. It's like everything's offset. All the weight, the lobe, and everything. So I'm not picking apart somebody's animation, just encouraging you to be a little cautious when you see an animation. All right. So one of the miracles is with that crankshaft, with that offset from the line of the crank, you can turn what type of motion? Reciprocating motion into circular motion. Isn't that incredible? That's not part of the study of this class, but probably in your mechanism class or other classes. It's a very simple mechanism, isn't it? The changing of reciprocating motion into rotational motion. You can also get to dictionary, online dictionaries, and you can see where they label parts. When I teach a class like this, I'll often say, okay, what are they showing here? They're showing you the block. And then what are they showing you with this fluid passage through there? There's some water with ethylene glycol antifreeze, so it doesn't freeze in the wintertime. You have a detached thing that's bolted to the block, which is the cylinder head, so the cylinder head up here. In the cylinder head, you have the spark plug. You'll have overhead valves. Here's two overhead valves operating with valve springs, poppet valves that push down. When they push down, they open up space for the flow to go around it to exit. So this would be the exhaust manifold, and then this would be the intake manifold, where the intake, the same thing, poppet valve, you push that valve down, now you have room to bring in the air-fuel charge. You have the camshaft, did I point that out, running up here? And it has little lobes on it, and when it rotates the right position, that lobe pushes down on that valve. Let's see what else. Oh, you have the piston, and there's usually a set of rings to help with the oil as well as the compression, like two compression rings to help seal it with the cylinder, and one set of oil rings. Some of them have more, some of them less. The piston moving back and forth, there's a wrist pin right here connected to a connecting rod, which actually is the bottom part right here where they bolt. And then the offset from the crankshaft, and then the counterweight is sitting over here. So you don't want to overfill your oil. Why? What's going to splash into the oil in the bottom? And then it's going to whip it up like that, right? You have an oil pump to push the oil where you want it. In cheap lawnmower engines, they actually do go down and dip in and splash it up. They don't have a pump. They splash it out of the bottom. All right. Now that you've been exposed, this is what I like to do. I say, here's the number or letters for all the parts, maybe when I was doing clickers, and I say, where's the crankshaft? And the students have to look, and they have to, where's the crankshaft? Is A the crankshaft? Pointing, no, that's the camshaft. Where's the crankshaft? G? H. H, it's H, isn't it? All right. Where's the connecting rod? G, right? Where is the cylinder head? Yeah, I kind of pointed that out. You have to find these things, but it's over there at L. And it's a little hard sometimes to trace the little line, but it's L for this illustration. Where is the intake valve? Yeah, so it's right here. Notice it's slightly cooler color than the reddish hot exhaust valve going out. And so that would be D is kind of the best call for what the intake valve is. And then the camshaft. A, that's the camshaft. That's the way I learn. I think that's the way most people learn. They test themselves. They read something, they close the book, they say, what can I remember about what I just read? Or they cover something up and say, which of these, what's the name of each of these parts? So the 4-stroke cycle. Let's talk about each of the strokes. There's 4 strokes. You can start with either one in the series. Let's start with, compression stroke. So think about this. I like to use my fist and image, the piston going up and down like this in a cylinder. And I think, okay, compression. Here is the top with the head. Here is my cylinder. The piston starts at the bottom, and it moves to the top. And that's the direction the piston moved during the compression stroke. True? And what they do is they call this top dead center. At the top of the at the top of the stroke, the piston comes to rest. It's not moving anymore. Okay, and then it started with the bottom dead center. So it started at the bottom, went to the top. That's a stroke. That's the compression stroke. After the compression stroke, we have what is the next stroke? Well, the piston's going to move from the top to the bottom. And what happened in between was we had a spark that fired, that created the combustion. And I know that the spark plug fires a little before top dead center, and it takes a while for the fuel to burn. And the logic in the internal combustion engines adjusting that all the time, depending on the load and the RPMs and things like that. It's adjusting it where it starts to fire as it gets closer to top dead center. How many people know standard time, when you used to have a timing light, have to set these things? Did anybody ever had a timing light and ever set an engine? Do you remember the degrees before top dead at what RPM with the vacuum disconnected on the vacuum advance? Like 12 degrees or something? 13 or something? I think you're missing out on a whole lot of education. Get a timing light. You don't even need them now, do you? You don't even need a timing light like you used to. You used to use it all the time. Okay, but the thing is for our model, we're going to think, it gets to the top dead center, then it's combusted immediately. And it takes no time for it to combust the whole thing. And now you have something that was air-fuel mixture. It was under high pressure and temperature because you compressed it. But after combustion at constant volume, what do you think about the pressure and temperature now? A lot higher. And now it's going to push that piston down in the power stroke. And as it pushes it down, it's our standard boundary work, pushing back the face of the piston. And then when it reaches bottom dead center, You can't expand it anymore. So what type of stroke is going to follow after you get to bottom dead center? You're going to go back up to top dead center, right? What is that stroke? It's exhaust. So you think, oh, I have this exhaust valve. It's going to be open. And what are we going to be pushing out? The exhaust products. All right. Then we're wanting one more stroke to get us back to the start. So we're going to start at top dead. Piston's going to move down to bottom dead center. And what's going to be happening? What's the name of that stroke? Intake stroke. And so the exhaust valve, what do you think about that exhaust valve? Oh, it's closed now. But what valve is over here? The intake valve. And what's coming in as you pull that piston down? The fresh air-fueled charge. And is it going to be in a state of vacuum compared to atmospheric pressure? You has to be, unless you have a turbocharger or supercharger, or naturally aspirated internal combustion engines, which is 99.9 something % of the engines out there. They're not turbocharged. Some of you may own one. But basically, it's drawing from atmospheric pressure across that air filter, through the ductwork, through the intake manifold, and now finally a little pressure drop across that intake valve, and so it's a state of vacuum. The intake manifold's a state of vacuum, and the cylinder is an even higher state of vacuum to get it to come in. All right, now you're ready to repeat. You see that? Isn't that the 4 strokes? How did I learn the 4 strokes when I was young? I just sat there and memorized them. They have to come in order. Doesn't matter where you start. You could start with the intake, then the compression, then the power, then the exhaust, or whichever stroke you want to start with. So let's talk a little bit about those valves. Which valves do we have? We have the intake and the exhaust valve. So think about, this is the intake, this is the exhaust. What is the position of those valves when you're undergoing the compression stroke? Are they open or closed? Both of them are closed. How about for the power stroke? Is the intake open or closed? Closed. Exhaust? Closed. Now we have a little action, right? For the exhaust stroke, what happens to the exhaust valve? Opens, but the intake stays closed. And then during intake stroke, the intake's open and the exhaust is closed. So there you go. So we talked about the position of the piston. We talked about the names of the strokes. And we talked about the valves. Okay. Now, the other thing to talk about is I'm going to try and do it over here. PV diagram, pressure volume diagram. And I'm going to put a line in right here, which is atmospheric pressure. And we already talked about the pressure in the cylinder can be and needs to be less than atmospheric pressure. That's why I put the atmospheric pressure in right there. So let's place it during a starting point was during the compression stroke. So at the start of the compression stroke, is the volume large or small? Should I put it over to the right or to the left on the x-axis? At the start of the compression stroke. To the right. It's a large volume. It's starting, where is it starting? At bottom dead center. So I have a large volume per kilogram of air. So we start over here, and we're starting around, let's say a little over around, well, put it a little bit under atmospheric pressure because we just finished the intake stroke. But as soon as you are starting to compress, guess what's happening to the pressure? Quickly above atmospheric pressure. And as we compress, it'll do something like this. Now, I know that I just talked about firing the spark plug at perfect top dead, but the spark plug actually fires a little bit before you get to top dead, which would give you the smallest specific volume, the smallest volume. All right? So we're going from the volume that's the largest to the volume that's the smallest. Either you think about cap V, total volume, or you think about volume per unit mass. Either one works. Okay, but as you get closer, then the spark plug fires. What do you think the pressure does? It really goes up. Then what happens? You're starting to expand, but there's no more air-fueled mixture to combust, so the pressure's coming down. And as you come down, you get over to here, and then whatever valve, so this was spark plug fire. What is it right here? A valve opens. What type of a valve opens? When the exhaust valve opens, there's a massive outrush, and it drops dramatically down to essentially atmospheric pressure. And that's why you have a muffler. I said that. It's a big pop out. Actually, it's easy to have Mach 1. It's choked flow, trying to get around there. Okay? But a lot of mass will pop right on out initially. But then you still have the piston at bottom, dead center, full of exhaust products, or products of combustion. So what do you want to do? You want to make them exhaust products. So you push them out. If you're going to push them out, are you going to be pushing them out at slightly over atmospheric pressure? Yeah, you got to push them out past the exhaust manifold or through the exhaust manifold, through the catalytic converter. You got to push them out through the muffler, the tailpipe, and then finally push. So it's got to be slightly above atmospheric pressure. And then what closes? The exhaust valve closes, the intake valve opens. So there's two valves doing a switch right then at top dead center on the exhaust stroke. And now you're going to be ingesting air-fuel mixture. What does it do? It drops to a vacuum. We're below atmospheric pressure. And away you go, and there you go. That's a PV diagram. If I had a good pressure sensor, maybe I'd put the pressure sensor somewhere in the head, and it's essentially the same pressure throughout the gas. It's just one pressure inside that piston cylinder assembly. I don't have any shock waves. It's quasi-equilibrium. Then that's the pressure that I measure. That's a PV diagram. Make sense? All right. So this illustration I've shown for years, but I can't find it anymore on the internet. It's old. But it was actually, I even know, it was like before Google was big. You know, you could find things in the early 90s without Google or something. Anyway, some institute in Germany, you can see it's not in English. And it was a very interesting simulation because they showed you the strokes going back and forth of the four-stroke spark. There's their little spark plug, and then intake and exhaust valves. And they also showed you, and it moved, the little dot moved on the PV diagram, showing you the whole sweep. I thought that was just one of the best illustrations. I can't find it. If somebody can find it and send me a link to it, that'd be great. But it was a little klutzy because it was so old, you know. But I thought it was one of the best animations. You could find me another animation like this. You send me the link. I'd appreciate it. All right? But it's not just the pistons moving back and forth. It's actually in sync with the PV diagram being swept out. The point was actually moving. This ZZ point or whatever point actually moved. And so you could really see it together. And you could slow it down and then speed it up and slow it down so you could capture everything. Now we move to some analysis of the real system. Well, the real system is complex. We could do a good job of analyzing it, but we have to make some simplifying assumptions. So what? So why do we do these? So we can make the calculations doable, using the skills and the tools that we have developed in this class. So we focus on a fixed amount of air, pure air, that's trapped in the piston cylinder assembly. No humidity, water vapor, no fuel in it. The air is always air. It's never converted to carbon dioxide and water vapor that are the standard products of combustion. Air always behaves as an ideal gas, so we know PV is equal to RT all the time. And that U is a function of temperature all the time. The internal energy is a function of temperature all the time. And enthalpy is a function of temperature all the time, not a function of temperature and pressure, just a function of temperature. This is a review, Thermo 1. Combustion process is replaced by heat transfer. So we just take the piston on a PV diagram. We still have this concept of bottom dead when you have the largest volume, and top dead, and you compress it, and when you get up here, it just sits there at the same volume, and you replace the combustion by just adding heat. And as you add heat, the temperature goes up, the pressure goes up, but the volume does not change. That's our simplification. We have no intake or exhaust, so it's a closed system, trapped amount of gas. So you just go through the power stroke, and now down here you replace the intake and exhaust processes by just a heat transfer at constant volume to close it. You see how that's approximation to the real PV with the pressure during exhaust and pressure during intake is sort of neglected. And now this is our cycle. That's our air standard analysis of the Otto cycle. And all the processes are internally reversible. So no entropy generation during each of the processes. So we go from a state 1 to state 2 to state 3 to state 4 back to state 1. Those are our 4 states on a PV diagram. Why do we introduce this? Again, so we make the calculations doable. There's an additional cold, every now and then you'll see cold air standard analysis. That's everything above with the additional assumption that the constant specific heats, you use constant specific heats, usually you just pick them off at either 298 Kelvin, 25 degrees C, or 300 Kelvin. There's not much difference between the two. And in our book, we have a line for 300, but not a line for 298. So often I say cold air analysis at K of 300 Kelvin. So you use C sub P, C sub V, and K, all are constants. And that makes the calculations even, how do you like that? More doable. True? So the Otto cycle, the one I just described, we want to be able to sketch out to go from state 1 to 2. This right here goes from V1 to V2, from state 1 to state 2. What is this process? I know that's a stroke. That's a compression stroke. And in our internal combustion engines, we talk about the compression ratio. R is the symbol used in this book without a subscript. R is our compression ratio, and it's the volume change experience. So it started with a large volume, V1. It ended with a small volume, V2. And internal combustion engines, there's things that we quote. We say, oh, these are the specs, the specifications of my internal combustion engine, right? Okay, help me a little bit. Who wants to volunteer? Say, I know that I own an engine in my car and I can tell you a little bit about it. Like, how big is it? Who knows the engine, how many cylinders it has? 8. Who has an 8-cylinder? All right, you're my volunteer. How many liter or cubic inches? 5.3 liter. V8, 5.3 liters. Somebody else? 4.6 V8 or 6? It's a V8 at 4.6. All right. 5.7. 5.7, 8. Who has a 6-cylinder? What do you got? 3.2. I got a 3.8 in a Buick. That's a very common Buick 3.8 liter 6-cylinder. Very good engine. Made for many, many years. Who else has a 6-cylinder they know of? Who has a 4? All right. How big is your 4? 2.0 liter. 2.4. 1.5. Really small, but they're usually pretty good for efficiency. I have a 2.4 4-cylinder in another vehicle I have. And we had a 1.8 at one time in a little Honda. I don't think it was a 1.6 liter. I think it was a 1.8. What did you have? 2.0. Very common. 2.0, 2.2, 2.4 for a 4-cylinder, right? A friend of mine has a Chevy Suburban, and for a number of years they put these humongous, I don't know why they did it, and I think it's an 8.1 liter. It's like almost 500 cubic inch. It loves gas stations. But it has no problem pulling whatever you want to pull. 4-wheel drive, Suburban, 3/4 ton. Man, just hook it up and go. Make sure your hitch is strong. The frame, the chassis, everything is strong. Just make sure your hitch is strong. I think it's got 12,000 pound pulling capacity. So anyway, but what's the compression ratio? We know typically, a lot of people know how big it is, displacement volume. They know the number of cylinders, but does anybody know their compression ratio?
12 to 1.
12 to 1? Yep. So he's got a 12.0 compression ratio, 12 to 1 or 12. Either a single number or they put it something to 1, like 8.5 to 1 or 9.5 to 1. Anybody else? Used to know this more. But with the engine electronics and things, NOx sensors especially, there's been less, at least when we were young, when I was younger, years ago, people would know their compression ratio. It was a bigger deal. With that type of compression ratio, you have to buy the high octane fuel. Do you remember what your minimum octane is? 93. Ouch. Yeah, okay. Anybody know if they have to buy the minimum octane above the 87? You do? What do you got, Jay? You have to use premium? Do you use mid-grade or the high? The which? The high, the 93? Okay. Isn't it 93 the highest? What's the middle? And then 87 is the low, typical? 91-ish? Okay. Anyway, so that's your compression ratio. And now, when you get to here, you undergo that constant volume heat addition. Sometimes we'll put it like this. There's my heat addition from 2 to 3. And then from 3 back to 4, that's my power stroke. And then from 4 down to 1, that's my heat rejection out of the cycle. So what we want to do is we want to analyze the complete cycle by 4 independent processes. So the process going from 1 to 2. Write the first law. For a trapped amount of air in a piston cylinder assembly that's just undergoing the process from initial state 1 to final state 2, you would say, oh, let's put it on the per unit mass basis, so lowercase q, 1 to 2. That'll be kilojoules per kilogram. That's how much heat is coming in during that process, minus the work out during that process, equal to U2 minus U1. Those are both lowercase or specific internal energies. And we're going to neglect changes in the kinetic and neglect changes in the potential energy. True? Is that a good first law or not? You like it? Very good. I do too. Anybody else like it? All right. Can you write it then for process 2 to 3? So it would go Q 2 to 3, work minus work 2 to 3 is equal to U3 minus U2. And then 3 to 1, 3 to 4. Q 3 to 4 minus work 3 to 4 equal U4 minus U3. And then 4 to 1, and this is the tricky one, Q 4 to 1 minus work 4 to 1 equal to, at the end of the process, I'm at state 1, and at the beginning of the process, I was at state 4, so it's U1 minus U4. True? If we sit and we just sum all the Q's, what do we get for the cycle? Q net. If we sum all of the W's, what do we get? W net. Will these two be numerically equal? You bet they will be. Otherwise, look for my error. If I sum all of the changes in the U's, so I'm going to sum this plus this plus this plus this. What do I get? 0. Because U1 cancels with the U1 down here. I don't know if I want to mess up my diagram. That cancels the U1. And then this U2 cancels that U2. This U3 cancels that U3. That U4 cancels that U4. So the sum of all the changes in internal energy for the cycle has to be 0. It went through a cycle. All right, now that we got that refresher straightened out in our mind, what about which of these 3 terms, either the Q, the W, or the delta U, is 0 for the first process from state 1 to 2? Q. They're right. They're exactly right. Why is Q 1 to 2 0? Because it's adiabatic compression. And if it's adiabatic, reversible compression, guess what is constant during the compression process. What is the symbol S for? Entropy. Entropy is constant during the compression process from 1 to 2. All right, now 2 to 3. Work is 0. Now, why is that work 0? No change in volume. I have to have boundary work. I have to move the piston. All right. Now, from 3 to 4, which one is 0? Q. And what is constant? Entropy, isentropic. And then 4 to 1. So a lot of these terms drop out. But if I said, I want you to calculate work 1 to 2, how would you calculate work 1 to 2? It's pretty good if I can get it equal to the negative in the change of the U's. Typically I use the first law to calculate my works and my Q's. So if I wanted to calculate the works and the Q's, really what I really need is I really need to boil it down to T2 minus T1. I need to get the temperatures, because if I use constant specific heats, isn't this C sub V times delta T? Isn't this also, this was U2, isn't that C sub V times T3 minus T2? Isn't this C sub V times T4 minus T3? And isn't this C sub V times T1 minus T4? So if I want to get my Q's or my W's, I first get my temperatures, and then I have it. Make sense? Somebody says this. They say, Professor, during the process from 1 to 2, is volume constant during the process for 1 to 2? Okay, you have a mistake. You just put C sub V. What does that subscript on the C mean? Constant volume, specific heat. Manteuffel doesn't know what he's talking about. I'm learning from an idiot. This is disgraceful. I want my tuition back. This is just one of those many challenges of why thermodynamics sometimes stumps students, because you sit there and say, am I just contradicting myself? Can I really use C sub V, specific heat, constant volume, for a process that's not constant volume? Yes or no? You are correct. You can say yes, and you can say it with confidence. But there's a long story to back it up. And sometimes when people on the internet, flame off, he doesn't know what he's talking about, he just used C sub V and blah, blah, blah. It's like, I don't have time. Go get the book and read and learn. All right? Do you want me to invest a minute to try and answer that question more concretely so that you can answer it concretely? Let me give them a minute, and then if you still have a question, I'll do it. All right, insert, new page. What is the definition of C sub V? No matter if it's liquid, no matter if it's superheated vapor, no matter if it's two-phase liquid vapor, it doesn't matter what's the state of the substance. What's the fundamental definition of the property C sub V? The rate of change of U with respect to T holding the other property, V constant. That's what the definition is. That works for steam. That works for refrigerants. That works for gases, real gases. That works for ideal gases. Oh, now we want to apply it only to an ideal gas. What do we know about an ideal gas? Well, we know 3 things. Can you memorize them? Did you memorize them? What are those 3 things? Somebody says, this is an ideal gas. This is what I know is true about an ideal gas. PV is equal to RT. Not sometime, all the time. What else? U is a function of temperature, all the time. And the last, H is a function of temperature, all the time. Of those 3 things, which are going to be used right now? The middle one. The middle one. So let's take this piece of information and put it into C sub V is equal to the partial of U, a function of temperature only with respect to temperature holding V constant. Do I really need to hold V constant if it doesn't depend on V? If by definition, if it's only a function of T, it don't matter what V is. So the partial derivative turns into another derivative, which is called the Ordinary derivative. Aren't you embarrassed? All these math classes. How many people want to take another math class in their life, right? No way. No way. Come on. Didn't you take it? How many calculus? How many calculus classes did you take? Count the engineering analysis in there too. Man, it's ridiculous. So now I have this is a simple ODE. Man, too many acronyms, Professor. ODE stands for? And you just want to separate and integrate? So you just separate and integrate. So you say du is equal to c sub v dt. And you integrate. And then you get, from state 1 to state 2, from state 1 to state 2, you get u2 minus u1 is equal to integral c sub v. But if c sub v is a constant, I love those type of integrals. Come on outside the integral. And it's c sub v t2 minus t1. Boom. I'm not saying it's trivial. I know there's a lot of math and a lot of physics, a lot of thermodynamics behind this, but it is justified, and that trips students up because they say, this is not a constant volume process, but I'm using c sub v. Let's go order some jumbo shrimp, right? It don't make no sense. So there you go. Okay. So now the same thing over here, you just do it all through the system. So the key is to get the temperatures. So let's solve a problem. Or no, I just did all this, didn't I? The only thing I didn't do is plot it on a temperature entropy diagram. So if we plot it on a temperature entropy diagram, and we're going to start with adiabatic compression. If it's adiabatic, so Q is equal to 0, and it's reversible, sigma 1 to 2 is equal to 0. What is S2 minus S1? The same, or the 0. It's the same S's. So we're going to go from 1 to 2. Remember, you're going to compress it. It's going to get a little hotter. From state 1 to state 2, boom. Now, the little trick is you have constant volume heat addition. Entropy's going up, and volume's equal to constant out to state 3. And then you have constant entropy expansion in the power stroke back to 4, and then constant volume here. So we have kind of 1 to 2. What was constant? S equal to a constant. 2 to 3, 3 to 4, and 4 back to 1, and S equal to a constant. Make sense? Now let's solve a problem. Oh, I don't have time. I'm so sorry. I've got to give you back your exams, and we're done for today. Thank you.